today we have Daniel Su, and he's going to present to us his paper on transformers, parallel computation, and logarithmic depth. He's a professor at Columbia University. Yep, thank you for being here today. You can take it from here.
Thanks everyone for coming and for the invitation to speak in this forum. So I'm happy to be presenting this joint work with my now former PhD student Clayton Sanford, who just graduated, and Matus Pelgarski from NYU. So the context for this this research is trying to get better theoretical understanding about transformers. For this forum, I assume everyone quite familiar with a lot of the developments in this area. We know a lot of things about transformers over the past several years now. In various guises, they are some kind of universal approximators, Turing complete architecture model for computation. But when you start limiting their size or complexity, we know a lot of computational limitations that they have. And so this, this is what you expect from a new model of computation. But the same can be said about a lot of other neural architectures that are used in modern machine learning, and where we're trying to, get a better understanding is to figure out what is it that distinguishes transformers from these other kinds of neural architectures. So this is just a slide to get everyone on the same page as to notation. It's not too important exactly the details here, and but I'm going to be talking about transformers, which at the basic unit is a self-attention head. So a self-attention head is always going to be processing a sequence of n elements, and every sorry, this should be the ith outcome of the ith output of the self-attention head is just a kind of combination of value function applied to the inputs, and these kind of combining weights are given by softmax of these collection of inner products between a query, the query function applied to the ith input, with the various key functions applied to the different n inputs. And so in this talk, I'm going to be pretty lax in terms of what I think about as self-attention head. In particular, the embedding functions are going to be allowed to be arbitrary functions that just embed some element into m-dimensional vector space. Okay. A self-attention layer will just be a sum of h of these self-attention heads, and a transformer is just a composition of L such self-attention layers. Okay, so here I'm just thinking about a transformer as this L depth L network of self-attention layers, and the width of every layer is h. And I'm not going to be worrying about precision so much during the talk, and everything should work as long as the numbers are log n precision and all the alphabet sizes of poly n size. Okay, this is just the technical notation for this talk. Important thing maybe is just that the thinking about both the width, the depth, and the embedding dimension as the main measures of size for a transformer. Okay, so what is the goal of this work? The goal is to try to use parallelism as a way to distinguish transformers from other architectures. Now, of course, parallelism is very natural when you think about a transformer as a circuit model. But here we want to get a little slightly more fine-grained understanding of transformers and how parallelism is kind of crucial to understanding them, especially when you kind of restrict the width of the transformer. So the way we are going to do this is in two parts. The first part is going to first relate transformers to another model of parallel computation, that of massively parallel computation. And I'll introduce this in the first part of the talk and say exactly what I mean by relating these two models of computation. And then in the second part, I will kind of take a particular problem, which is this so-called K-hop induction heads problem that we kind of derived from people may have heard of as induction heads, and use that to separate transformers from some of the other architectures that you might have heard of. So that's the outline for the talk, and so I'll just get started with the first part. Feel free to stop me if there are any questions at any point. Okay, so the first part, I want to introduce transformers, this massively parallel computation model related to transformers. So MPC, this massively parallel computation model, is really kind of the culmination of a bunch of different theoretical models that people in the distributed computing community have been developing as a way to understand these kind of modern parallel computation architectures like MapReduce, Hadoop, things like that. So here's kind of the basic way to think about the model. So it's going to be a model for processing inputs of size n, and what MapReduce, Hadoop, and all these systems were designed to do was to process extremely large input, extremely large objects, so large that they can't even fit on a single machine. So what's going to be important is that we also parameterize the memory size for any machine, or the storage, or whatever single machine has access to. So we'll say that the number of machines is Q, and this memory size per machine, let's say in words, is just S. And S is going to be something that's sublinear in the input size n. So n to some fractional power delta being some fraction between 0 and 1. Of course, somehow the input is going to be distributed across all Q machines, and at least the total memory size should be big enough to store the entire input. So n should not be bigger than Q times S. Okay? But S otherwise could be quite small, like n to the 0.01 or something like that. And so the way the MPC model proceeds is that first the input is distributed across the Q different machines. And then each machine can do some processing on its own local memory, the input that it has in its local memory. And then a round of communication will take place. So in this round of communication, every machine can send messages to all the other machines, but it must be the case that the total number of bits, or words in this case, that's sent by any single machine is no more than its memory size S. Okay? And at the same time, no machine can receive more than S words, otherwise no way to store it. So a massively parallel computation algorithm has to ensure that this kind of communication constraint in each round of communication. Now, and the MPC model doesn't talk about what happens within a single machine, how it processes its local memory, and this we're going to allow the machines, at least in terms of the lower bound, to do arbitrary computation. And usually, when you design algorithms, often you try to make that an efficient algorithm as well. We're not going to be worrying about that. So really, the main complexity, once you set up the parameters of the model, is how many rounds are needed to solve a certain computational problem. How many rounds of this kind of interleaving between local computation and communication do you need before you can solve a computational problem? Okay, so that's the MPC model. Maybe already you're starting to see some analogies with transformers. Let me just say that there are MPC algorithms developed over the past decade or so for many different problems. So problems as simple as broadcast, sorting, prefix sum, a lot of graph problems have also been solved in the MPC model. And what's notable about all of these problems is that the round complexity is kind of it's very small, just constant, independent of the problem size for a lot of these problems. And that's really the gold standard in MPC. For some of these more complicated problems, like connected components or minimum spanning force, only recently or relatively recently have people been able to develop kind of constant round algorithms, at least for certain subclasses of problem instances. So maybe the round complexity will be parameterized by the diameter of the graph. So in these two results, the round complexity is just log diameter. Okay. There's a lot of relationship between this model and other models of parallel computation. But in this particular model, one thing that people have been struggling with is figuring out if there's kind of sub-logarithmic round complexity algorithms for a lot of basic graph problems, and in particular connectivity. Okay, so this is one of the major open problems, and we're going to get back to this in a bit. Just to give you a flavor of what an MPC algorithm might look like. So here's the problem of broadcasting a word to all the other machines. So you think of the input as somehow one of the machines get a particular word and the other machines get nothing interesting. And you would like that first machine would like all the other machines to know this particular word. Now, if you try to just have that machine send that word to all the other machines, this might exceed the bandwidth restriction, right? The memory size is n to the delta for some very small delta, and there's lots and lots of machines, as they call it in neo and machines. Sending the single word to all the machines in one round might be too much. But a very natural thing from the theory of distributed computing that you can do is to set up these broadcast trees with some kind of largish fan out. And here we just make a order S array broadcast tree. And this turns out to be able to solve the broadcast problem in constant number of rounds. Basically, the number of rounds will be just the depth of the tree, and you can kind of just work out what happens with this B array tree, where B is roughly S. You would just get a constant number of rounds needed to solve this broadcast problem. Okay, so that's a kind of an example. That's an example of the kinds of things you can do in massively parallel computation model with very, very small memory per machine. So, okay, so what does this have to do with transformers? So let me tell you about two really deep thoughts that we had. Saying that, a little bit jokingly. Kind of very natural things to start wondering about. So the first is that if transformers can simulate massively parallel computation algorithms efficiently, then whenever someone has designed an MPC algorithm, an efficient MPC algorithm, then that implies that there's also a small transformer for solving the same problem. I'll get back to the second deep thought in a bit. So we already saw that there are a lot of efficient MPC algorithms for various problems, like broadcast sorting, so on, connected components, so on. So we were hoping that there seems to be some, at least pictorially, some similarities between MPC and transformers. Maybe this is a little bit deeper than that. Maybe every MPC algorithm can actually be efficiently simulated by a transformer. And so this is the first result that we have in our paper. So let me just kind of walk you through it. So the result says that if there's some function, that's a problem that you can solve using a R round MPC algorithm. Okay, so R is the number of rounds that the MPC algorithm runs for, using a number of machines Q. That's actually, I think this can be a little bit larger than n, but let's say it's at least 1 minus n to the 1 minus delta, and every machine has a small memory. Let's say n to the delta or some any delta. Then the same function or same problem can be solved by a transformer with the size of the transformer kind of being very efficient relative to the complexity of the MPC algorithm. So the number of layers will just be proportional to the number of rounds that the MPC algorithm runs for. The width, the number of attention heads per layer will be very small, log n. And the embedding dimension is relatively small compared to the size of the memory of each machine in the MPC algorithm. So remember, if n to the delta with the size of the memory for every machine, then the embedding dimension we need is n to the 4 delta times the log factor. So, when delta is small, this is what we're usually thinking of with MPC algorithm, that they work with very, very small memory machines, and you can solve these computational problems in that architecture. Then in the computational model, then this theorem tells us that there's also going to be a corresponding transformer that does the same thing, and the size will be roughly the same as the way of measuring complexity for the MPC algorithm. Okay. So as an example of the corollaries, now if you want to talk about designing transformers for determining connectivity in graphs or sparse graphs, you just import these existing results from the MPC literature and get kind of small size transformers for solving the same problem. Okay, so that's the first way in which MPC and transformers are related. based on that the first very deep thought that we had. Any questions about this before I move on? Okay, so yeah, so there's a lot of algorithms that designed for MPC. Oh, I should say that a lot of algorithms in MPC are designed to be fully efficient. That is, that they work with any memory size. So basically, for any delta here, and delta constant delta bigger than 0. But maybe for some problems, we only know how to solve them with, like, let's say, I don't know, like square root and memory um, uh, per machine. Then there's a bit of a blow up here that would not be great. This is like more like the S, kind of like S to the 4. So this would be kind of not such an interesting transformer, because now the embedding size has to be as large as the entire input. But modulo this issue, this is a fairly efficient simulation. Okay, so that's the first result that we have that connects transformers to MPC. And then the second one is kind of in the reverse direction. Okay. So the thought is that if massively parallel algorithms can simulate transformers sufficiently, then any problem that was supposed to be hard for MPC should also be hard to solve using a transformer. And so actually, it's a little bit easier to think about what the first part of this statement is the if clause, that if MPC algorithms can simulate transformers. And you might think that, of course, they can simulate transformers. Probably Google, OpenAI are definitely using parallel algorithm to serve up your large language model results. So maybe like empirically, we know this should be probably possible, but this also turns out to be true theoretically. So if you're given any problem or function that you computed by a transformer with L layers, H heads per layer, and embedding dimension M, such that this total with M times H is not too big, let's say some small power of N into some delta, then we can construct an MPC algorithm that does the same thing. Basically, it's going to simulate that transformer, the large number of machines. And the number of rounds of the MPC algorithm will, again, just be proportional to the number of layers of the transformer. That's what we had in the other direction. The only thing that's kind of suboptimal here is that or at least it's not clear if it's suboptimal, but the only thing that doesn't look like it scales that well is the number of machines has to grow quadratically with the input size. Okay. But otherwise, the number of rounds is roughly what you would hope for, and the memory size per machine is very close to what you'd hope for, just proportional to the embedding or the width of the transformer. Okay, so that tells you, this result says that MPC algorithms can simulate transformers. So anything you could do with a transformer, you can basically do also with the MPC algorithm. But we wanted to use this in a way that kind of would explain what's hard for transformers. So what problems are hard for MPC? And what the idea is that this theorem will let us transfer hardness for MPC to hardness for transformers. Okay, so turns out after a decade or so to research the MPC, the community of people working on MPC have kind of come down to a particular problem that seems to be at the heart of difficulty for MPC algorithms, and that's this so-called 1 versus 2 cycle problem. Okay. So in this problem, an algorithm is given a graph, let's say a sparse graph, and actually the sparse graph is promised to be either one of these two different graphs. Either it's just a cycle on n vertices, or it's the union of 2 cycles on n over 2 vertices each. Okay. You're just given one of these two graphs. The nodes are not labeled in some obvious way for you, but they'll promise to be at least one of these two different graphs. And your job is just to decide which is which, okay, which one it is, if it's connected one or the disconnected one. And this is the instance of connectivity that seems to be hard for MPC, in the sense that no one has been able to come up with an MPC algorithm for this that runs in number of rounds is smaller than log n, okay? At least when the memory size is strongly sublinear in n. So the hypothesis here is that every MPC algorithm for this problem, if it uses, memory that's strictly sublinear, n to the 1 minus epsilon for some epsilon, and any polynomial number of machines, then no matter, how many machines you have, the number of rounds of this algorithm has to grow at least like log n. So this is the hardness that seems to be that people believe about the belief for MPC. And what our theorem lets us do is to transfer this to kind of a hardness result for transformers. So the corollary is that assuming this hypothesis, every transformer that has total width, embedding size times number of heads, smaller than n to the 1 minus epsilon for any epsilon bigger than 0. And it's supposed to solve this connectivity problem, then the depth, the number of layers has to grow like log n. So I think this is, a very concrete problem that says that even if the, even if the, even for, fairly large width transformers, there's a lower bound on the depth that it must have. And of course, it's a conditional lower bound. It's not unconditional. It's based on this, assumes this particular 1 versus 2 cycle hypothesis. So depending on, how much you want to believe these researchers in working on distributed computing, this is either good news or maybe a challenge for you to do better in designing MPC algorithms. Okay, so that's the way that we're kind of thinking about transformers as kind of a parallel architecture. A little bit different from just standard circuit complexity because here we're not thinking about very, very wide transformers. We're looking at what happens when the width is usually something more like a small power of n rather than arbitrary polynomial in n. But once you kind of restrict the width of transformers this way, it seems to be a fairly tight connection to massively parallel computation. In the sense that efficient algorithm for MPC gives us small transformers, and transformers have the same kinds of difficulties as MPC algorithms. Okay, so that's at least our way of thinking about why transformers are kind of, you should really think of them as this kind of parallel architecture. And now want to move on to the second part where we kind of explore a little bit more look at a specific problem that where transformers can really take advantage of parallelism, but other architectures aren't able to do this if they don't have the same parallel processing power. And that's this K-hop induction head problem. Okay, so induction heads is kind of a term that people attach to something that people were finding this paper from OpenAI also et al. They identified this kind of mechanism in some existing pre-trained transformers, and they interpreted it as solving a particular kind of next token prediction task. So here's an example of what that task looks like. I don't really want to define it super formally, but you're given this kind of sequence of tokens and you're asked to predict what comes next. Okay, so you have the previous sequence and then you need to, based on the sequence, predict what should the next token be. And what one of these induction heads would do, it would predict as follows. It would predict B. And why is that? Because the last token that it sees is A. And what should follow A now? Well, you just look back in the sequence at the last time you saw the token A, and you predict what comes after that. And then in that case, it would be. Okay, so that's the so-called induction heads task. And it seems like a very simple to describe task. Formalize this fairly easily. We're actually going to look at an iterated version of this task that we call the K-hop version of the induction heads, multi-step induction heads task. So it's again another kind of next token prediction problem. Now, of course, the one hop one would just be the standard induction heads task. So again, if you're given the same sequence, you would just predict B. But in the two hop or in general K hop version of it, it's going to be a different answer. So in the case of K equals 2, the idea is that you should apply this same mechanism iteratively, say K times, not just once. And in this case, if you apply it twice, you would predict C, because you would first apply, you look at the last token and look at the last time you saw that token, what followed it with B, and then you apply the mechanism again to B now at that particular B. And the last time you saw that B, it was a C that followed it. So in this case, you would predict C. Okay, so this is, it's easy to define these iterative uh, tasks. Why is it interesting? Well, some of my colleagues here at Columbia came up with a very nice interpretation of what this multi-step version of induction heads test might be interpreted as. So you're given these kinds of word puzzles, like the prompt might be Jane is a teacher, Helen is a doctor, and so on. You list a bunch of people with professions. And then you start listing other things, like the mother of John is Helen, the mother of Charlotte is Eve, so on. You say who's the mother of who. And then finally, you ask a question like, what is the profession of John's mother? And so in this case, you have to do this two hop induction heads thing where you see John. Well, the last time I saw John, it was telling me who the mother was, Helen. And then the last time I saw Helen, telling me what Helen's profession was doctor. That's how you come up with the answer doctor. Okay, so that's this kind of multi-step reasoning problem. I think it's fairly natural and at least simple to describe. But the importance for us is that it's something that transformers can compute quite efficiently, again, exploiting parallelism in an important way. And other architectures, at least these so-called non-parallel or more sequential type architectures, seem to have a lot of difficulty with it. And we'll make this precise in this part of the talk. Okay, so maybe it's already evident that transformers can solve the one-hop version of this problem because people kind of found it in the wild. But the K-hop version of it is not that much more difficult because you can exploit this parallelism in a very strong way. So here's our result for this particular, this K-hop version of the induction heads test. It says that for any K, there's this. Okay, so this, of course, is a kind of a sequential prediction problem. So it makes sense to just use these causally masked transformers where your prediction only depends on, at any given position only depends on the previous position. Okay, so what our theorem says is that for any K, there's a causally masked transformer where the width is constant size. So M and H are both constant. In that case, it's just one. And the depth is just logarithmic in K. Like we can really make it like get the exact number here, which is 2 plus log base 2 of K. And such a size transformers is efficient to solve this K-hop problem, to compute these K-hop predictions at all positions of the input sequence. And the idea here is that we're going to be, the solution actually was really inspired by this work by Bietti et al. From Europe last year. It really exploits parallelism in a very strong way. The idea is that we're going to solve the, let's say like the first one-hop induction heads tasks, not just for the final token, but for all tokens simultaneously. So you get all of these arrows and pointers in one round, okay, maybe like 2 rounds or something, of kind of two-layer transformer to do this. And then every additional layer is going to actually double the reach that we can get to. And so this is why you only need log base 2 K layers of a transformer to be able to solve the K-hop problem. This is kind of a, it's not difficult, especially when K is a power of 2. When K is not a power of 2, you have to be a little bit more careful, but kind of a fun exercise to do. Actually, I think what's more surprising is that in our paper, we report some results of trying to actually train up transformers to solve this K-hop prediction problem. And so, of course, using some nothing fancy, just standard PyTorch packages. And empirically, what the solution that was found is pretty much the same as the solution that we kind of hand designed to solve the problem, with almost exactly the same, maybe even exactly the same number of layers that was going to be sufficient. Like if you use, one layer too small, like let's say only 1 plus log base 2 of k layers, it wouldn't work so well. But once you get to like 2 plus log base 2k layers, then it worked perfectly. Somehow the solution we came up with is kind of made some sense the natural solution that SGD would find. Okay, so this is just saying that transformers really exploit parallelism again to solve this otherwise problem that otherwise would have seemed kind of like a sequential problem. But these non-parallel architectures really struggle here. And here's kind of the way we're going to show this. So you take any kind of very non-parallel architecture like an RNN. In fact, even these like multi-layer RNN things like Mamba and so on. As long as the state space is not the state that they maintain is not too big. So what we show is that any such architecture, any such model, in fact implies a kind of communication protocol, and this kind of restricted form of communication setup in a distributed computing environment, where kind of the parties, you have k parties, and they kind of have to communicate in a particular round robin fashion. So and then kind of this is kind of a well-worn trodden path where you show that in fact problem that you want to solve is hard in this communication model, and therefore hard the computational model that you had that you kind of reduced to communication this way. So it turns out that the K-hop problem is going to be hard in this particular communication model, and this is a consequence of some recent work from the streaming algorithms community, in particular this result by Asadi and N in 2001. So Asadi and N, they are people working in streaming algorithm. They don't exactly work on problems like K-hop, but it turns out problem that K-hop very closely resembles is a problem that's very, very well studied in communication complexity, and especially with applications to streaming algorithms. And that's the so-called pointer chasing problem, nicely formalized by Nissan and Richardson in '93. So let me tell you about this problem and show you why it's, or at least hopefully you'll see why it's related to K-hop. So the pointer chasing problem actually maybe is parameterized by K here. You're given a K layered graph. So in this graph, you have, let's say, K plus 1 collections of vertices, each of exactly the same size. So N over K plus 1 vertices per layer. And then the edge sets are going to be between consecutive layers. So EI will just be a perfect matching between vertex set I and vertex set I plus 1. So you have this so-called layered graph. And the problem is you're given some vertex in the first layer, and you want to figure out which vertex it's connected to in the last layer. And since this is a perfect matching between consecutive layers, it's exactly one path from any vertex in D1 to vertex in D K plus 1. And so your job to figure out which of the, in fact, I think the way it's written is usually just to determine if it's an even or odd vertex in vertex K plus 1. So that's the problem. And it turns out you can encode such an instance of this problem as an instance of the K-hop problem. Okay, basically, the kind of roughly in reverse order, the edges the edge sets will kind of show up in reverse order in this sequence. And so that when you solve K-hop for this particular sequence, it will be the same as figuring out which vertex the start vertex is connected to in the final vertex set. It's a fairly I think efficient reduction from uh, this pointer chasing to k-hop. And I'm potentially I can go into the details of exactly the communication model and the lower bound for this problem. But let me just tell you the corollaries of the that we get from the lower bound of Asadi and N. It basically says that there's a bunch of average case lower bounds for computing these k-hop predictions. So even for kind of a relatively benign distribution, some kind of uniform distribution over k-hop instances, at least that arise from the pointer chasing problem, a bunch of different what we call non-parallel architectures have some lower bound in their resource that either grows linearly in k or like n to some power in their size. So here's a couple of examples of the lower bounds that we get. So if you take any of these kind of recurrent neural networks, like even these multi-layer ones, either the number of layers has to grow linearly in k, much worse than a transformer, which is log k, or the state space size has to be large, like n to the k to the sixth, and n over k to the sixth. So think of k as some smaller power of n, n to the 1 over 12 or something, and then this is saying that s will have to grow kind of large with like root n. Okay, so this is kind of similar to the type of lower bounds we had given in some previous works for RNN on problems that transformers seem to solve quite efficiently. But this doesn't just apply to recurrent neural networks. There are other kinds of architectures that seem to be very sequential. And an example that's not so obvious is these kinds of approximate self-attention versions of transformers. So you take a transformer, but you don't actually use the self-attention network. You use some kind of low rank approximation to the transformer or to the self-attention unit. Okay? So if you use one of these, I think these are called like kernel former or various things like that. So if you use such a transformer with like a low rank self-attention approximation, again, you get a so-called lower bound of this form. Either the depth has to grow linearly in k, or this width times the rank has to be n over k to the sixth. So again, if the rank, basically the rank should also grow with some kind of power of n. Can't hope for the rank just to be the constant and keep everything just as small as what you had with the original transformer. Okay, so that's this low rank approximation to self-attention versions of transformers. And again, and then we finally show a lower bound on, for very shallow transformers, to say just a single self-attention layer, but you're going to help it along by giving it this kind of ability to write stuff down, like in the chain of thought models. So if you're allowed to write down T tokens, chain of thought tokens, either T has to grow linearly in K, or the width has to be like n to the k to the n over k to the sixth. We show a bunch of other lower bounds for various other architectures, but it's basic idea is that all of these architectures are effectively kind of giving you some kind of sequential communication protocol, and we know that's even in that sequential communication model, solving this pointer chasing problem or the k-hop problem has to be hard. Okay, so that's really all I wanted to say about the k-hop induction heads task. People are interested, I can tell you more details later. So we find this problem to be quite simple and natural. Some nice interpretations of what it might be useful for. And the way it seems like that, at least us as humans were able to come up with solutions for this problem using a transformer really exploits parallelism. And in fact, it's kind of the same solution that we get when we train transformer to solve this problem. And I didn't mention this before, but this kind of log k depth is actually necessary. Again, conditional on that 1 versus 2 cycle hypothesis. So you shouldn't expect like a constant depth solution to solve this problem, unless the width is extremely large. And then this problem does seem to separate transformers from these other kinds of what we're calling non-parallel architecture, unless their depth is much worse, exponentially worse than what was required with transformers, or their size is kind of very large. Okay, so that's really all I wanted to say. Again, the main feature we kind of wanted to focus on in this paper about transformers is parallelism. Okay. One thing I think that's different about this work compared to some other works is that we are really relying on logarithmic depth and this kind of sublinear width regime for transformers, a little bit different from um, kind of existing work on uh, trying to understand the computational power of transformers. Um, and the way we are able to separate transformers from other architectures in this regime is, I think, exhibited by a fairly natural problem. Of course, this is there's a lot of future work that left to do. One thing that we are completely ignoring is the complexity of what happens inside of these embedding functions, other than the bit precision that numbers that they deal with. And there turns out to be some issues with doing this. In particular, some positive results that you might get using this connection to MPC would imply that somehow the size of these embedding functions might need to be extremely large. So this is something that we're interested in looking into further. And then, of course, I didn't say anything about learning. These are all just kind of hand constructions and maybe some empirical observations about what happens when you try to train transformers. It would, of course, be nice to understand if any of these solutions can actually provably be found by efficient learning algorithms. Okay. All right, that's all I really wanted to say. Thanks for your attention.